Okay, welcome to Chemistry, Module 15, Part 1. A little different this time. I've got my new stylus, so now it's with stylus. Hey! That means that you don't have to try to squint at my whiteboard on my video. It also means videos are a little easier to upload. As usual, if you have any questions, just email me at mrc@mrcscience.com. As with all these videos, you should probably have your book handy, so if you don't have your book, go ahead and get it. And I'll get started, so just stop the video and grab your book if you need to. Okay. So, what we're talking about this week, or at least the first part of Module 15, is chemical equilibrium. Now, we talked before that I tell you, every once in a while they tell you lies in this book. Here's one of the lies they told you. So in here oops, grab my right thing here. In your book they have an equation. Nitrous dioxide gas plus carbon monoxide gas gives you nitrous oxide gas plus carbon dioxide gas. Pretty straightforward. Everything here is balanced. Where they told you the lie is right here. The right arrow. This means your reactants all become products. Well, guess what? That's not true. Sometimes, under certain conditions, it can go the other way. So our arrow could face that way. Or there are times when it will reach what's called equilibrium. And equilibrium is when the forward reaction is proceeding at the same rate as the backwards reaction. And thus, some reactions you will, but some reactions you will never get rid of all of the reactants. They will still go back and forth a little bit. Many reactions are heavily weighted towards the product side, which is what we're looking for. But so in chemical equilibrium, that's what you're looking for. If you got your books, go ahead and turn to page 526. And in here is a table. So on this table, you see a graph. On this side, you got molarity. Molarity per second is what they're putting. So they're doing a reaction rate. On this side, they got time. So when you start out, your reactants are way up here. Or your forward reaction, your arrow going this way. Everything, you got all reactants, very little products. Everything will go and it will start going down as it uses up those reactions. Once you start the forward progress, once you have products, you're going to start the reverse reaction. The reverse reaction will pick up speed until they meet and they reach equilibrium. So where the forward and reverse are the same rate. That's when we reach equilibrium. That's when we got our little double arrow there. So, okay. Experiment 15.1, I never do in class because it is super messy, but if you want to try it at home, you can. Just do it someplace where you can clean up the mess. Get rid of that. Basically, what they do is they take two 2-liter jugs, they poke holes in them, cut the tops or the bottoms off, turn them upside down, and then you just fill up one, and then you quickly start filling the other ones. You catch the water in the cups and you go back and forth until the water levels in the 2-liter jugs reach equilibrium. It can get very, very messy, so if you want to try that one home, go for it. Let your parents read it first and do it someplace where you can clean up the mess, preferably outside. It's nice out. So, okay, so let's talk about reaction rates. First thing we're going to talk about is something called the equilibrium constant. Now, we know our standard setup for a reaction. Oops, grab my paintbrush. Plus B gives us C plus D. Oh yeah, we should take care of our little lie here. Now we're going to see more and more. We're writing it like this. Goes both directions. So you're familiar. Here's our products. Our reactants. Here's our products. And somewhere in between you get an evening out of the reaction going this way and the reaction going that way. So based on certain temp, this is for a certain temp, there is a reaction constant, K. Looks like they use a capital K for this. Our reaction constant equals, now this will look a little familiar from last module, concentration of C, to now we're going to actually use this stoichiometric coefficient, or lowercase c, concentration of D, to our D, using that coefficient, all over concentration, of A. I'm still getting used to this stylus, so hopefully my writing will get better as we go. Concentration of B, the B power. So basically we got your products divided by your reactions, your concentrations, and multiply or taken to the exponent of these stoichiometric coefficients. So that is the equilibrium constant. We're going to use this quite a bit this module. Go ahead and turn to page 530, and in here you'll see two examples. The first one they show, here we'll just write it out here quick. Getting used to this. So they got a reaction of N2. We're not going to worry about gas right now. This will come into play though. We want to make sure we know, but everything here is gases. And it's going to give us 2 nitrous oxides gas. So everything here is a gas. We'll talk about why that's important in a little bit. So they say write out your equilibrium constant. So it's K. K equals. Then we got the concentration of our products. So we got our only product is NO, nitrous oxide, but it's got a stoichiometric coefficient of 2. So you want to make sure your equations are balanced for this. Then over the concentration of the reactants, we got a concentration of N2 times the concentration of O2. Stoichiometric coefficients are 1, so it doesn't matter here. So what they do then is they give you some concentrations here. So concentration of NO is 4.51 molar, and that is squared over 0.35345 molar, yeah, 54 molar times 0.124 molar. That's going to give us a total of 463. Now, units on stoichiometric or equilibrium constants are interesting. They can change. Now, if we look here, we end up with m squared here. We got an m here. We got an m here. So these two m's cancel out, and that m squared cancels out, and there are actually no units on this constant. That won't be uncommon, so don't worry about it if you don't get any units. So that one's pretty straightforward. Let's look at the other one. So let's go. I just got to lift and click. There we go. I'm just going to delete that. Whoops. Go back, grab my brush. Okay, so our next reaction is a little more complex. I got 4 ammonias, NH3. It's a gas again. I'm not going to worry about that at this point, but it will become important in a minute. 7 O2s gives us, again, we're looking for equilibrium. 4 NO2s, 4 nitrous dioxides, plus 6 waters. Everything's a gas. Actually, for this, water being a gas is very important. We'll learn that in a second. So let's write our equilibrium constant here. We got K equals. Now we want the concentration of our products on top. So we got the concentration of O2. Its stoichiometric coefficient is 4, so we want it to the 4th power, times the concentration of our H2O. Again, its stoichiometric coefficient is 6, so we want the 6 up here, over concentration of our NH3, which is to the 4th power, and concentration of our O2, which is to the 7th power. So you can see they run the numbers through here. You can get your numbers using their concentrations, but I mainly want to show you how this is set up with this 2.8 times 10 to the 4th, negative 6, sorry. Negative 6. Now let's look how they got their units. If we add this all together, we got, everything's in molarity, so I didn't put in molarities here. But we got 4 plus 6 is m to the 10th over 4 plus 7, m to the 11th. They cancel out on top. We're left with 1 over molarity. So that's our units. Okay, that should make some sense to you, hopefully. If not, you can always drop me an email. We can do more, but as we work our way through here, it should make more sense to you. I'm going to leave this up here right now. Here, let's see. No, I'm not going to play with that. Okay, so what does the equilibrium constant mean? It means that when the reaction reaches equilibrium, when the forward and backwards reactions are the same, at that point, these are going to be the concentrations of your products and your reactants. So that's what the final concentrations are going to be. Not everything's going to go away. There are times when one will become extremely small, but that says what's going on. So now what happens here, since up top here we got our products, grab my right pen, we got our products over our reactants. Then, if our reactants get really small, if we got really small reactants and really big products, that means our K is going to be really big. It's going to be much greater than 1. It's going to be very big. That means that mainly, if K is really big, very large number, in fact, much larger. Here, we'll just go about that. Much larger than 1, then that means that we're going to have almost all products, and you can write the arrow like that. If our products, nice thing here is Control Z is your friend, okay. If our products over our reactants, now if our reactants are really big and our products are really small, then our K is going to be very small. In fact, a lot less than 1. In which case, our arrow is going to go towards the reactant side because we're going to end up with a lot more reactants than products. If they're about equal, our K will be equal to 1 or relatively close to 1. If that's true, that means that there is no strong product or reactant, and that's when we're going to use an arrow like that. So if you look on page 532, it kind of lays that all out for you. So, we're looking at, that's what the equilibrium constant tells us. So we can say, well, with this reaction, we're going to get a lot of products, or this reaction, we're going to actually get a lot of reactants. Or we're going to come to about equilibrium. Then as a chemist, you can decide how you want to proceed in making your material. Okay, so let's do this. I'm going to rewrite, or no, we're not going to write that up there. Okay, so now let's talk about phase, or not phase, state or phase. If it's a gas, oops, once again grab my pen. So if we're a gas, everything's good. If we're aqueous, everything's good. If we're a solid, it is not included in the reaction. Now, if you think about it, this makes sense. So if there's a solid in the reaction, let's see if they give me an example with a solid. Oh yeah, they do. Okay. In the book they give us 2 sodium hydroxides, little I, which is aqueous, plus magnesium chloride, which is also probably aqueous. Yep. A lot of our chemistry actually happens aqueously. And we've got magnesium. It gives us magnesium hydroxide, which is a solid. And sodium chloride, which is aqueous because it's ionic, it dissolves in water. Now what happens is, as this solid forms, it precipitates. You probably heard of the precipitates. One of the jokes in your book is if you're not, or I don't know if it's in your book, it might just be a regular joke. If you're not part of the problem, or not part of the solution, you're part of the precipitate. So what a precipitate does is it drops to the bottom. So it is hard to react with, so it's hard to go back the other way. Once it's a solid, it's hard to bring it back into solution. So, in fact, it's near impossible. So what happens is this concentration stuff just leaves. So our K for this would be our products, and we don't use magnesium hydroxide because it's a solid, so our K here is just our sodium chloride over our reactants, sodium hydroxide to the second power, and magnesium chloride. Both of those are aqueous and can be included. So when we generate our K, we ignore magnesium hydroxide because it precipitates out. Okay, hopefully that makes sense. If not, again, just drop me an email and I'll talk about it. If enough people are interested, I'll do some more work on it. Okay, so solids are not included. This one's a little less obvious, but guess what? Liquids are not included. The reasoning behind this is a little less obvious, but it's what works. So when we're working with equilibrium constants, we only care about gases and aqueous. If you turn to page 534, can't write, 534, you'll see how the solid precipitate drops out of the solution. So solid will continually drop out. Okay, so those are the rules for that. If you want, so what do we do with it, basically, is the next thing. So we can use that to tell whether or not a solution or if a reaction is in equilibrium and whether it has to, what it has to do to go to equilibrium. Equilibrium has not been reached yet. So if you know the equilibrium constant is 463, like we had the one, if you take the concentrations of everything and you find that the equilibrium constant calcs right now at 200, that means it has to go up. Remember, it's products over reactants. So if that's true, that means we need a greater number, so we need more products. So more products will be created, less reactants will be created. If it happened to be 560, it was over, the reverse would happen. Our products would need to go down, our reactants would need to go up. So it would tell you which way it's going. Not super useful in chemistry. It's hard to take molarities of a reaction while it's in progress. So, but it's another useful thing. Okay, so now let's get to something called Le Chatelier's principle. Some French guy came up with this name, Le Chatelier, or the Chatelier's principle. So, what they do here is they once it's reached equilibrium, they add something else to it. So if you got your books, turn to page 534. Down near the bottom it says Le Chatelier's principle. When a stress such as a change in concentration, pressure, or temperature is applied to an equilibrium, the reaction will shift in a way that relieves the stress and restores equilibrium. Kind of scary mouthful to say. If you look at the graph above it, this kind of explains it. Now, right now, we're not going to deal with pressure and temperature. All we care right now about is concentration, what the molarity is. So, if we have your forward reaction, which is your products up top, here, let's write this out here a little bit. Whoop, oops, grab my mic one. Whoop, whoop. So we got this, and it reaches equilibrium. These are your products, these are your reactants. You start with probably 0 reactants in all products. So as your products reduce, reactants increase, you reach equilibrium. Now what happens if you suddenly drop in more product, one of the products? Well, what happens is the concentration of your products go up. Whoop, that's not a very straight line. But then it's got to find a new equilibrium based on concentration. Products and reactants. So it's going to adjust, and how you find that out is you take your new, say you change the concentration of A, or not A, if you change the concentration of, oh, I have this backwards, sorry. This is reactants, this is products. Products, reactants. So if we add more of our A reactant, if that goes up, then your K, which will be your A to the A, B to the B over C to the C, D to the D. If this concentration goes up, if that number changes, this is going to change this one. This number is going to go up as well. So that should make some sense to you. So next week we're going to deal with how Le Chatelier's principle changes with pressure and temperature. Again, if you have any questions, email me at mrc@mrcscience.com.